Here are solutions to homework set number 1 for ECE 376. This homework set is just kind of a background on the PIC microcontroller that we're using. The PIC can measure voltage to 4.88 millivolts. It can measure time to 100 nanoseconds. What does that mean? What are the capabilities of the PIC processor? It's actually pretty impressive. That's one of the reasons we use this processor in the class. It works really, really well for low-level programming. The first page on the solutions, here's a quick summary of them. I'm going to be going through each problem one by one on the solutions here. So the first problem is a PIC can drive up to 25 milliamps on the I/O pins. If I connect a load to it, such as here, what's the smallest R2 can be? Well, if you take 5 volts over 25 milliamps, the PIC outputs either 0 volts or 5 volts, logic 0, logic 1. At 5 volts, 25 milliamps implies 200 ohms. So the biggest the resistance has to be is 200 ohms. I can have any load as long as it's more than 200 ohms. What that means is if you want to drive a speaker, build an annoyatron, annoy your friends and neighbors, you can't drive an 8 ohm speaker directly. The PIC can't handle the current. To drive a speaker directly, I need to stick a resistor in series to limit the current to 25 milliamps. That'll reduce the volume, but that's really all the PIC can do. If you want more volume, you need to add some buffering circuit like a transistor, op-amp, H-bridge, stuff we'll cover later. But whatever the load is, the PIC can only see, the smallest that the PIC can see is 200 ohms. Suppose I have an ohm meter, problem 2. Suppose this is nominally 2000 ohms. What is the voltage I'm going to see here, and what's the smallest change in resistance that I can detect? Now what that means is the resolution on the A to D is 4.19 millivolts. How much does R have to change so that the voltage changes by 4.19 millivolts? Well, to do that, first find the voltage at 2000 ohms, 3.333 volts. Add, 4.88 millivolts, make that. Add 4.88 millivolts to it. The voltage has to change by 4.88 millivolts, or increase to 3.382 volts for the PIC to see it. Going backwards, the resistance that corresponds to 3.382 volts is 2008 ohms. So that's the resolution. It changed by 8.8 ohms. The resolution on the PIC, on the analog input in this case, is 8.8 ohms. Problem 3. The PIC can measure time to 100 nanoseconds. How small is 100 nanoseconds? Well, if you go to the X-Men universe and look at Quicksilver, the fastest of the X-Men, Quicksilver can run 2,050 miles per second. How far does Quicksilver travel in 1 clock? Well, 1 mile is 1,600 meters. 2,050 miles per second. Convert miles to meters times seconds. The seconds cancel, the miles cancel, and I'm left with meters. The result is 0.33 meters. The fastest X-Men moves 0.33 meters in 1 clock. Or 330 millimeters. That's, if you're an X-Men fan, that's impressive. If you're not an X-Men fan, you probably don't care, but us X-Men people, X-Men fans, are really impressed by that. Problem 4. Suppose I start going faster, approaching the speed of light. If I do that, time's going to slow down. How fast do I have to travel so that time slows down by 1 clock over the span of 1 year? Well, using Lorentz's equation from Wikipedia, here's the time shift. Doing a Taylor series expansion, the time shift is roughly 1 plus 1/2 b squared over the speed of light squared. The delta t is roughly 1/2 b squared over c squared times the change in time. If that's 100 nanoseconds, this is the time span I'm looking at, 1 year. 1 year is 31 million seconds. times 1/2 velocity squared over speed of light squared. Plug into the numbers, winds up being 23 meters per second, or 53 miles an hour. If you travel 53 miles an hour, due to relativity, you're going to lose 1 clock every year. Not a lot, but it's small enough that the pick can actually see it. And it's not a very high speed. So we actually do run into relativity. With the clock of the pick running at 10 megahertz, I can start seeing relativistic effects at 53 miles an hour over the span of 1 year. Problem 5. If I have a 555 timer set up, what this does is I charge and discharge the capacitor. It's going to charge up to 2/3 of 5 volts, discharge down to 1/3, 2/3, 5/3. That's the voltage at the capacitor. The output is a square wave, 0 volts, 5 volts. The period is a function of R1, R2, and C. Equation for it is the period. There's the equation. There's the equation for the period. R1 plus 2R2 times C times log of 2. Let's see. So if I start out, the square wave has a frequency of 6.86 hertz. The smallest change in frequency I can detect is when the period, right there, changes by 1 clock, changes by 100 nanoseconds. So this is the frequency. Add 100 nanoseconds to it. Here's the new period. Whenever the period is the frequency, here's the new frequency. Take the difference. The difference is 0.000004 hertz. So if I measure time, the pick can measure change in frequency of 0.000004 hertz at 6.8 hertz. Really, really impressive. Basically, computers can measure time really accurately. If you can convert something to time, you can measure it insanely accurately. Problem 7. Suppose in that 555 timer, I vary the resistance. How much can R2 change? Does R2 have to change so that the period changes by 100 nanoseconds? So here's the equation for the period. If I increase t by 100 nanoseconds, recalculate R2, R2 winds up being 10,000.007 ohms. There's the resolution. It goes from 10K to 10.007. The pick can see a change in resistance of 0.007 ohms at 10K. Again, pretty impressive. Suppose R2 is a thermistor. How much does the temperature have to change so that the resistance changes by 0.00072 ohms? Well, plugging in R, solve for T, temperature changes from 25 degrees to 24.9998 degrees, or a difference of 0.0016 degrees Celsius. So I can measure temperature to 0.00016 Celsius using a PIC processor. Again, really impressive. The processor we're using in this class is actually a pretty impressive processor. With it, I can measure frequency to 0.0000004 hertz, resistance to 0.007 ohms, temperature to 0.0001 degrees Celsius. All for $8 for this processor. And that's homework set number 1. Just to give you an idea of what the processor is capable of, have some respect for the PIC processor. It's pretty capable. And that's homework set number 1 for 376. Give me a little bit of background on the PIC processor.